Hello, everybody. Hey, hi. Let's see. Well, I found your sign error, Lyle.
Oh, yeah? Where?
Yeah, equation doesn't have a number, but in section 4.9.1, I should probably number that equation because we use it. But the sign is off on my definition of the Poisson bracket.
So it was not my mistake then?
It's not your mistake, it's mine. You got me.
All right.
Lyle 1, Jim 0.
Now it's tied up. It's 1-1.
We're tied up. Okay, fair enough. Let's see here. I'm trying to find it. There's caramel. Let me see here. Trying to find where we were.
Guillermo will probably be pleased to take some credit for finding that error too.
Which one?
Minus sign that you were mentioning in the Poisson bracket.
Yeah, the definition.
Oh yeah.
What section did I say?
Oh god. I
4
mean,
point, hang on. Where I write out the Poisson bracket of f and g, two functions.
which one? The first one or the second one?
Let's see. Okay, equation 4.1 is correct.
Oh yeah.
When I wrote it for the complex field, the overall sign's wrong.
Yeah.
So yeah, that would have been down in 4.8 or something, right? Where did I write that out? Anyway, yeah, I got the sign flipped. Sorry, my bad.
Page 128. That's where the problem starts.
Yeah. Okay. Yeah. Here
Yeah.
Okay. Yeah. There. Okay. So yeah, 4.9.1 in the current version. But yeah, page 129 is what it's on now. I'm continuing to edit, making some changes. I've made the metrics all consistent through the first part of the book, things like that. Yeah, let's see. It's right now, except I haven't posted it on Canvas. I'll get this posted on Canvas after class. And
So it was the
latest.
Poisson brackets with the Hamiltonian or Hamilton's equations, or checking for Hamilton's equations. There's the sign errors in those, one of those four.
Yeah. So at the beginning of problem one, like a half page into problem one, I write out the Poisson bracket for f and g in terms of a complex field, and it should follow the same pattern as position and momentum. X with p is IH bar, right? So x first, p second. So the partials would be ddx, ddp. So for fields, it's dd phi, dd pi, or del, it's functional derivatives, but phi first, pi first for the positive signs. And that should be true all through. That means that the time evolution is the function with h, so h is second. I mean, all of these things are subject to definition, and you try to make it all consistent, but it sometimes gets away from you. So I've corrected that. I will post the current version of all this after class today, sometime this afternoon.
I have a question.
I guess we don't need to meet now.
What's that?
I guess we don't need to meet now because that was.
Okay, because we've resolved it. Yeah. Okay. Yeah. Sorry. Yeah. I got this great example of how annoying signs can be. Mubarak and I are working on this research project. We're using spinners to describe some complicated space, and we're looking at self-dual fields, and you can project self-dual fields with these are antisymmetric, so you need an antisymmetric identity, alpha mu, beta nu minus what would it be, delta alpha nu, delta beta mu, plus or minus. I think there's a quarter on all of this. Doesn't matter. But Levi-Civita, alpha beta mu nu. So with the right normalization, that's a projection operator, and it will project into things that are self-dual under epsilon, anti-symmetric matrices. So if an epsilon on it gives the same thing back, that's called self-dual. And if it gives minus the same thing, that's anti-self-dual. Well, it turns out when you do this with spinors, there are two other things you can do. You have plus or minus projections, and we're going to see these guys, one plus or minus gamma 5. And it turns out that that also projects into some kind of self-dual things. And then there are things called the Tuft matrices, like this. Let's call this Ij. That are, there's something like epsilon Aij plus or minus, and then some delta functions here, A4 delta Ij. No, AI for J, for I, there's something like this. All right. All of these project into self-dual and anti-self-dual, but these guys act on anti-symmetric 4x4 real tensors. These things act on Dirac spinors, 4 components, complex vectors. And these guys act on, basically, these map antisymmetric tensors to 2 copies of SU2. And sorting out the signs between these. So knowing that the self-dual under this is the same as self-dual under that is the same as self-dual under that is a nightmare of signs. It takes about a half a day to work through and check it. But anyway, yeah. So more and more you will become aware. Hey, Eli, how you doing?
Hey.
Signs are an endless nuisance, rivaled only by factors of 2. That said, let's look at your problem. How's it coming? What questions do you have? Okay, so we've resolved that sign ambiguity. My apologies for the effort that went into that, but that'll work now.
So that's as far as I had gotten. I kind of ground to a halt there until I got that figured out. But so the next thing I have to do then is the solutions to the complex field.
Right.
The Fourier Transform.
Yeah, so you want to write the Fourier expansion for the field. And the only difference there from the real field is that the coefficient A, the conjugate is not A star, it's some B star. So you have twice as many Fourier modes. I think if you model it, if I get the notes right, and you model it on what I did with the real scalar field, it's going to be good practice for you to work through all those integrals. So was that a question or waving?
A question.
What's the question?
This is the question when you the annihilation and what's the other one called?
Creation and annihilation operators.
The annihilation and creation operators. I wanted to check because when you look at the self-contained commutators, they look exactly what you expect them to. But when I tested when the commutators, the A and B, the mixed ones, I got something that I wasn't expecting, and now I don't think this is right for me. So I want to check it with you.
Okay, so we're looking at the commutators of.
To be super specific, I want to check if I did the commutator for A and B.
The commutator of A with B. Okay.
Yeah.
All right. So let's.
So you got 0. I wanted to get 0, but I
got 0 for all of the cross commutators.
Yeah, and that's what I was expecting, but I got I delta, and so I was like, "There's no way that this is right."
Okay, so that is right. It should give 0, but maybe we should write it down. So we're looking at the commutator of A hat of K with B hat of Q, say, something like that.
Yeah, that's exactly right.
And well, so what was the Poisson bracket?
The Poisson bracket.
All right, this is a fundamental commutator, so it follows from the Poisson bracket of A of K with B of Q. So we can figure this one out and just infer that one.
Oh, really?
It-
Oh,
it's-
I just did it through calculation or evaluation through the integrals.
Well, yeah, okay. So once you've solved for, yeah, we have, sorry, I said it wrong. What we know are the phi and pi commutators, the phi star pi.
That's right.
And then we know these. So no, you're right. We compute these. So what is the expression for A hat of K? In terms of the
Scroll.
fields, what do you get? Yeah,
A
let's-
hat, it's phi plus pi dagger with some coefficients.
Pi plus pi dagger,
Yeah.
like this with, well, some coefficients, like what? Is there
Oh,
other
sure.
coefficients here?
It's worth a lot.
It probably.
Yeah, well, okay, fair enough. The omega square root of omega over 2 all in front, and then for the in front of the pi, it's I over omega.
Oh, I see. I've got them written out here.
Yeah.
Yeah, I did that to give you some benchmarks on the way, right? Just so you can do pi to 3/2. Then we're gonna do a Fourier transform.
That's right.
Yeah, there's a root omega over 2. That can actually come out. D3x of, okay, so then phi plus I over omega pi star. And these are functions of x. And then we have the Fourier mode e to the minus I kx. Okay, and then presumably you've got a b that looks similar, right? So b of, here I'll write it in terms of q, so 2 pi to the 3/2. I can't imagine this comes out looking too much different. This is omega sub q, that's omega sub k. D3x. So let's see what happens here. Yeah, what's this going to be? Is it the conjugate? What do you actually get for that? Oh, yeah, the conjugate. Okay, is my sign right there? What I have written is phi conjugate plus I over omega pi, but I'm wondering if this sign is right.
I mean, that's what I got as well. That's what I have written down.
Okay, Tyler, did you get that? Did you get it?
For B?
Yeah.
Or for B dagger?
This is B that
For
we're.
B, I got a minus sign there. Oh, wait. Yeah, no, for B, I got a plus. I got a plus there.
So there's a plus or minus here.
Yeah, it's a plus. It's a plus.
It's a plus. Okay.
Yeah.
Right. That's what I have in the notes. If that's wrong, I need to fix it. But you know, let's see. I got to catch up with the chat here. Racing to midnight. Okay. Chapter 4. Let's see. I think I'm working on chapter 6. So just as fast as you can catch up. Yeah. Yeah. Chapter 4. Okay. So we want the commutator of these guys. So these are going to be operators like that. And so if we commute these, A hat, B hat, okay, I'm going to have a 1 over 2 pi cubed. I'm going to have root omega q omega k over 2 coefficient. D3x prime. Let me call it y. Then let's see, what do we have? This is going to be a is phi hat of x plus I over omega of k pi hat star of x. Commutator with these guys, phi hat star of q, of, these are going to be y now, plus I over omega pi hat of y. And then out here, we're going to have the product of the two Fourier modes I, k plus q, kq x y, k dot x plus q dot y. Right?
Yep. That
Okay.
looks good.
Nothing
Yeah.
that matters.
Just two non-zero terms.
Yeah, so when this phi hits pi, and when this pi hits that phi, we're going to get something. And so when this phi hits that pi, we're going to get I over omega q, I think that one is. Then del 3 of x minus y, that's good. And we get a 2 pi cubed. Oh, no, we don't.
That's until later.
It's just that, right? Because this is the canonical.
An extra I though.
Sorry? Question?
Extra I, so it's I squared.
Why?
Yeah, you
This
get an I from
is
the commutator.
Oh, from the
It's a
time.
commutator. It's not a Poisson bracket anymore.
Right, so there's an IH bar there, good. Okay, so minus 1 over omega. And then this pi with that phi, I'm going to put a minus sign I over omega k. It's the canonical commutator is phi with pi. This is pi with phi, so I get a minus. Then I'm going to get an IH bar that's going to make this a plus. And then del 3 of x minus y. Like that. And that's all, right? That's what we get. Then we have e to the I, right? So k dot x plus q dot y here. These deltas are going to make x equal to y. Then I can do one of these integrals over the delta function and simplify it down. So 1 over 2 pi cubed. Then let's see, we've got, various omegas. Let me not worry about the omegas yet. Okay, do we end up with k equals q? I guess, yeah, we end up with some kind of delta. So all these omegas are going to turn into the same omegas. Then let's do a d3x. And now what do we get? I'm going to integrate dy. So I'm using those delta functions. So all of the y's are going to become x's. And all of the fields are gone, right? So I just have minus 1 over omega q plus 1 over omega k e to the I, whoops, careful. Okay, e to the I,
You were fine.
no, I'm sorry, it is common, isn't it? 1 over omega k. Then we have e to the I k plus q dot x. Okay, so
Yep.
now the integral over x is going to turn this into 2 pi cubed del 3 of k plus q. All right, now we do, right, that's the x integral. Okay, so we've got this thing times that stuff times the delta function. The 2 pi's are going to cancel. But the fact that we have a delta of k plus q means that in the preceding function, we can set q equal to minus k, because it's multiplying a delta
Shouldn't it
function.
be k minus q instead?
No, it's
It's
k plus
K.
q.
They were both.
Oh, they're both.
Same
Oh,
sign.
yeah.
So it is delta of k plus q. So I can evaluate this at q equal to minus k, but omega of k and q only depend on k squared, right? And so
All right,
omega
that was
of
my
k-
mistake.
So omega of minus q is the same as omega of plus q is the same as omega of k, right? Those all become the same. That's 0 right there. So
Yeah,
so
that
it
was
worked.
my mistake. It was I just kind of blindly put minus omega k instead of like realizing that it depends only on the square of the
Right.
k or q.
Right. Yeah. Lots of little points here, right? Just signs, factors, you've got to be careful whether you have a delta, because sometimes that delta of k plus q is going to make a real difference, right? It depends what you're looking at. If you have a q dot k somewhere, well, that's going to be a plus or a minus depending. So, you're right to keep track of that, but do remember that omega is positive square root of q squared plus m squared, or k squared plus m squared, but it just depends on k squared.
Thank you.
Okay, so there's an example. That was kind of quick, but it worked, which always amazes me. Are there any other questions?
Yeah, so for the final part, we want to, so prove there's a vacuum state that's not 2R, you can just follow the exact thing we did for the scalar field.
Yeah, I think it parallels right through.
Yeah, and then, so what do we do to describe the multi-particle states? You just apply the creation operators for A and B onto the state, and then it gives you a certain number of A particles, a certain number of B particles.
Yeah, you can show that the Hamiltonian is positive definite, right, on any state, the expectation of the Hamiltonian, so that if you lower with B or you lower with A, either way, you're going to hit a state that has 0. So lower all the way down to that state with A, and then lower with B, and you get a state that's annihilated by both of them. From there, you build up with A daggers and B daggers. They commute. You can put them in any order you want. They can depend on any wave vectors you like. So you build up all sorts of multiple particle states that way. And yeah, so we will see in the antiparticle commutation, like any minute here, that the B states are antiparticles. More precisely, even though Dirac took like a square root of the Klein-Gordon equation to get rid of the negative energy states, it didn't work. They're still there. So even in the Dirac equation, we have both positive and negative energy states. And that's an important part of the world, because that it's those negative energy states that become antiparticles when we look at them in our experience, right? You can think of those as negative energy states traveling backwards in time. All right, so have it clear in mind that interchanging past and future is a Lorentz transformation, right? That preserves the light cones. It's totally relativistic. So there's no preference in special relativity between past and future, nor is there in relativistic quantum field theory a preference. So we can have particles traveling backwards in time, and we're going to explicitly construct the green functions for the Klein-Gordon equation, and we'll see that there is a solution for the green functions that describes a combination of positive energy particles traveling forwards in time and negative energy particles traveling backwards in time. Now, this is not weird. imagine how you would experience a negative energy particle traveling backward in time. So here we are, we're moving up in the space-time diagram, you know, toward our future. We encounter this negative energy particle traveling backwards in time. What do we see first? We see the arrival here of some negative energy. Then later, we see the emission of some negative energy. How do we describe that? It looks as if positive energy is moved from the past to the future. Negative energy moving backwards, we experience as positive energy moving forwards. And the same is true of charges. If a negative charge travels, you know, a negative energy electron traveling backwards in time. So we see negative charge leave here, then arrive here. So this becomes more negative. Oh, now we're following its world line backwards, right? So this becomes more negative, and then this becomes more positive because the negative charge left it. We see a positive charge moving forward in time. That's the positron. So our experience of the positron is a positive mass particle traveling forward in time with positive charge. The spin gets reversed. All the properties get flipped from the regular particle state because we're experiencing them backwards in time. And that, let's see, have you guys heard of hole theory? I hope not.
Maybe.
It's wrong. They'll talk about hole theory and condensed matter classes and stuff because they're still living in 1930. But what I just described is the Feynman-Stuckelberg picture of the negative energy states, and that is the current view and the explanation for antiparticles. So we'll go through that in some detail. I want to ask, I'm still looking here at the last part of chapter 4, where I talked about the conservation of charge. Did I talk about that last time? We talked about the conserved charge, and then you make an operator out of the Nether current. So because you have phi star stuff, the complex scalar field action is invariant under a phase change. And there's a corresponding Nether current that's basically pi phi minus pi conjugate phi conjugate times some gradients. Where is it? It's one field times the gradient of the conjugate minus the same thing. So it's proportional to d mu phi star times phi minus phi star d mu phi. And there's an I and some other coefficients here, but basically you have this conserved Nether current when you do the standard Nether procedure for finding a conservation law corresponding to phase symmetry. And this happens with every complex field. What you then do is you look at J0 and integrate that over all space, and you call that some charge. And you use the fact that this is divergence free to show that ddt of this only depends on what flows over the boundary. Familiar story, I hope, by now. And so this charge is conserved. If nothing flows over the boundary, you always have the same amount of Q in a given volume. So now you make it all operators. And it's written there so you can read through it, but it turns out to be D3K. You've got some basic charge here, but you get an A dagger A minus B dagger B. And you see from this that these are number operators. You have a number operator for each wave vector K, and you sum over all those. So this is basically the number of A type things minus the number of B type things times the charge of any one thing. Well, think of that as a negative charge for the B stuff and a positive for the other, or minus that if you're talking about electrons. But anyway, you see that the total charge is the number of particles minus the number of antiparticles. So a nice picture consistent with what we're going to do here in the next chapter, where we really go through antiparticles. Does anybody want to see any more on that? It's the same kind of calculation you've been doing. You know, you take the normal ordered product of the operators and just work it out in terms of A's and B's, A daggers and B daggers. Okay, so now I want to look at what happens if you have a field with a source. So we're gonna go do a bit of classical field theory for a bit here. How much have you guys done with green functions? You're good.
Not a
Okay.
lot.
What's that?
Not a lot.
Not a lot. Okay. Hello. All right. So we'll do more. Okay. So, all right. So suppose we have box phi plus minus, yeah, plus m squared phi. So Klein-Gordon field here. But we have some source for it. There's some other field that couples to something that gives us basically a source. Now, the way to solve this is laid out very nicely in the Liouville theory chapter of Arfken's Math Methods book. So I certainly recommend that. But it's the green function technique. And basically the idea is to look for a solution when J is a single unit charge particle. And I'm still seeking a. So we can write this operator this way, but we're going to let this act on what's called a green function. And we're going to let that be a function of x and x prime. This is with respect to x. And what we want as a source is a delta function in x minus x prime. Think of that as a 4 vector. And let me put a minus here because for some reason I did that. Okay, so, oh, yeah, and I had a minus j up here, that's fine. Okay, so suppose we can solve that equation. This is called a green function. If we can find such a function, then we can solve the problem. Basically, a solution phi is given by integrating, right? All we're doing here is taking a linear superposition. So you put in the strength of your field, your source, and you multiply by the green function. I'm thinking of this 3-dimensionally instead of 4-dimensionally. Let's do d4x here. Okay, so if we write this, I claim that solves this equation, because if I act with box plus m squared on phi, then the integral is over x prime. So this operator comes inside and it only sees the green function. And that is minus del 4 of x minus x prime. So I do the integrals and I get minus j of x. Boom, solved it. Now, there are 2 issues here. One is you know, what happens with boundary conditions? Because you usually solve this equation with some sort of boundary conditions. There's a thing called Green's theorem, where in addition to this integral, you actually put something like, yeah. So if you include boundary conditions, you've got J with G integrated over the volume. Then I think it's minus the normal derivative of G over the boundary. If this is some volume, this is the boundary of the volume, times phi on the boundary, d3x prime. So you choose your green function to have vanishing boundary conditions. This is Dirichlet conditions. You guys have seen this in E&M if you've taken it. If you haven't yet, we'll do it next fall. But the boundary conditions are easily fit with this integral. That follows from Green's theorem. I'm not going to prove it now, but you can solve this equation with arbitrary boundary conditions on phi evaluated on that boundary. Once you solve this, and that's the second issue, how do you solve that equation? And happily, the source for that equation is 0 everywhere but a point. And so quite generally, you can build solutions. My phone keeps dinging here. You can build solutions from the vacuum solutions. So if you can solve the homogeneous equation, which you've just done, we've worked through that, then you can build G out of those solutions by taking products of the vacuum solutions, and you get this singularity basically by fitting some boundary conditions, right? It's only a single point, so you make that point essentially a boundary, and you let's see. My junk spam folder in my email. Yeah, no, my junk spam folder in my email has much less interesting stuff. Okay, so if you can solve the homogeneous equation, you can solve for the green function, so you can solve with any source and any boundary conditions. This is a beautiful technique, and we'll use it in quantum field theory too, where the four-dimensional version of this thing is it's like a Feynman propagator or something. There's another name for it in quantum field theory. Maybe not the propagator, but it's a Feynman something or other, right? We'll come to that. What I want to do now is solve for this guy for our Klein-Gordon equation. I'm going to solve with vanishing boundary conditions at infinity. So phi goes to 0, the boundary's off at infinity, so we don't need that term. I just want to find a certain basic property of the time dependence of the green functions. So in order to do that, I'm going to take a Fourier transform of this equation. So what does that look like? We need the Fourier transform of the Dirac delta. Well, we know what that looks like. And we need the Fourier transform of the green function. So we've got some g of k. Oh, let's see. Yeah, I may have to keep worrying about what dimension we're in. But yeah, no, this is going to be fine. If I write g of x and y, let's write it this way. So g of x and y is going to be a Fourier transform with the usual normalization. No, that's not the usual normalization, but let's go for it. Then we've got some g of k here, e to the I k dot x minus y. Sorry, x minus y. All right, four-dimensional dot product. Blech. Okay, so that's really K alpha, X alpha. And I'm going to put the minus sign here because I just want to keep, I want to stay consistent with the notation in my notes because it could be easy to get lost here. Okay, so that means that, oh, and we know how to write the del 4 of x minus y. We can write it the same way, 2 pi to the 4th. I don't know why I did the 4th here. I normally would do 2, but it's just the Fourier mode. K alpha, x alpha minus y alpha, d4. This is k, d4, k. Okay, so there are the Fourier transforms, and we're going to substitute that box plus m into the equation. So let's see. Box plus m acting on this, we're going to have 1 over 2 pi to the 4th. And in the end, it doesn't really matter. d4k. What normalization I chose here. But okay, so we're going to have box of this. Box of this with respect to x is going to pull down minus ik twice. So that's going to give us minus k alpha for the box, then plus m squared, then times the amplitude g of k. Then if I bring the delta to the other side, I'm going to have plus 1. And then e to the minus I k alpha, x alpha minus y alpha equals 0. Okay, all right, so not bad. Wow. Sorry, I'm gonna get this message off my screen. There we go. Yeah, that's right, good. So this is just a Fourier transform of the thing in brackets. And Fourier transforms are invertible. So if I invert the Fourier transform, it's going to show that the thing in brackets vanishes because the Fourier transform vanishes. And so I immediately have g of k is minus 1 over, or let's just say 1 over k alpha plus minus m squared. So that was easy. All we have to do is transform back.
Sorry, I'm not following how did G go from being a 2-argument to a 1-argument function?
It was just the way I wrote the product here. When we transform back, we can transform to a two-argument thing, x minus y. Let's see. Yeah, you could. In a way, y is fixed. Y is the position of the point charge. You know, pretend it's at the origin or something. So you just got some fixed offset of your x here. So we're really only transforming one variable. Frequently, g does turn out to be a function of x minus y, but in any case, we haven't done anything illegal here. Now, transforming back, right? So we can immediately write g, you know, it's this thing where, let's get some of the stuff out of the way. So now e to the minus I k alpha x alpha minus y alpha over k alpha minus m squared d4 k. So there's the answer. How do you do the integral? And it's a little tricky because it diverges, but you can make it converge pretty well. let's see, what we're interested in is in the energy part of this. So I can write this K alpha as K0 minus K squared minus M squared. Now, a straightforward way to solve this is by contour integration. All right, we extend to the complex plane. Well, I want to do the K0 integrals. So what we do is we extend to the complex K0 plane. And in that plane, we're integrating along the entire x-axis, the entire real axis. But what we can do is close a contour. So we're going to add a large arc that we push off to infinity in such a way that we can see that this integral along that arc tends to 0. And so basically we've added 0, but what we've done is to complete a full closed contour in the complex plane. And what's the name of the theorem? The Contour Theorem or something.
Residue Theorem.
What is it called?
Residue.
Theorem. Thank you. Yeah, Residue Theorem shows that that gives an easily evaluated thing based on the form of this. It gives you something at each simple pole. So basically, a closed loop integral around z minus z naught dz in the complex plane gives this, or let's put some nice function f of z up here. This is 2 pi I. If this is a counterclockwise circle, so positive phi direction, this is 2 pi I times f of z naught. And that's the residue theorem in complex analysis. How are you guys with complex analysis? So I think I recommended on Canvas chapter 7 of the gauge theory book. That takes it from z equals x plus iy, right? And just builds up basic results in pretty short order. So read that for a proof of the theorem. I guess I should look at it and see whether I put a proof of the theorem. It's not actually too hard. You can show that in the complex plane, deforming a path. If I've got some integral in the complex plane, I can deform that path any way I like, and as long as there are no simple poles like this in this region, I get the same value for the integral, because the integral around a closed loop with no pole in it is 0. Nice property of the complex plane. So the thing we need to do is write this thing as a sum over simple poles. This is, z minus z naught squared. No, that's, you need what are simple poles. First power of this goes to 0. But we can turn this into that by writing basically k naught squared minus k squared minus m squared. Let's call this stuff omega as positive square root of that. That could be handy, because then we can write 1 over k naught plus omega and 1 over k naught minus omega. And let's see, if I take the difference of those, probably this way, what is that? We find a common denominator. We multiply this up here, we multiply that up there. And because it's minus, it's the omega. So this is going to be 2 omega over k naught squared minus omega squared. Everybody agree?
Camera check.
Let's do this. So I'm saying 1 over k naught minus omega minus 1 over k naught plus omega.
Yeah, problem is we can't see. There we go.
Yeah, sorry. Okay. Find a common denominator. That's k naught squared minus omega squared. Then we have K naught plus omega minus K naught minus omega. And the K naughts cancel, the omegas add, so this is just twice omega over the denominator we want. So I can write this as a sum of two terms which are simple poles. So let's do it. Okay. By residue theorem, we'll get back to you. So I'm going to write this as 1 over 2 pi to the 4th. We've got this common integral, which is
That's like a partial fraction decomposition. That's the
yes, exactly what it's called, partial fractions. Yes. Let's see. I want tx minus ty here, minus k dot x minus y. If I expand that numerator, and then there's a d4 over 2 omega, and then we have our two poles, k naught minus omega minus 1 over k naught plus omega. Now, this is like the prototypic form for a contour integral, because you've got this exponential, right? So if we give k naught, let's see. So here we are in the k naught complex k naught plane. Now, if k naught is, suppose tx is greater than ty, so that part's positive. Then if k naught has a negative imaginary part, so we're envisioning something down here. Let's see, only that means we're going to be integrating that way. If I put a loop down here so that this k has a negative imaginary part, so k is equal to a minus bi, where a and b are some positive numbers, then e to the minus I a minus bi, just call it delta t. Delta t, I'm taking positive here. The two imaginary bits here are going to give me e to the minus b delta t. And then there will be a phase, e to the minus I a delta t. The phase doesn't worry us much. That's never zero. E to the minus b delta t, right, where b is the imaginary bit down here. We're going to let b go off to infinity. So we put this curve out at infinity. And at any finite angle, b is eventually infinite. So this holds all the way right up to epsilon from the axis. So we really are adding, in the limit as this b goes to infinity, we're adding something that is zero to the full contour. So, so that's what we're going to do here. But the thing that's important for what we're trying to show is that that works for t. This is for tx greater than ty. And so if the residue lies inside, basically anywhere in the lower half plane, then the residue theorem will give us something. If the pole doesn't lie there, then it doesn't give us anything. Well, the problem here is that the pole is on the real axis. And one of the many tricks in complex analysis is to push it off. So what I'm going to do is push the pole from k naught equal omega to k naught plus or minus I epsilon. And that'll shift the pole into either the upper or the lower half plane. And now I just apply the residue theorem, and it's straightforward to evaluate. But I can do that two ways. I can push it up or I can push it down. So which way do I do it? Well, I'm going to do it both. And one gives us something and one gives us nothing, so that's fine. If I push the pole up, then the integral around this loop is zero. If I push the pole down, then the integral around this loop is the residue at that pole. Then I take epsilon back to 0 and I get some result. So that's one of the poles. Then there's the other pole. That was right. That was this pole, right? K naught minus omega. So that's a pole that's close to K naught equals omega. But then there's another pole at K naught is minus omega, and we push that one off the up or down too. So we're actually going to get 4 candidate green functions, and we have to add one from each pole, right? We to have a full solution to this, we need to evaluate the integral at this pole and subtract it from the integral at that pole. So that gives us 4 different potential green functions. Well, the final green function is the sum of one of these two with one of those two, basically. Or we could even take linear combinations depending on boundary conditions. But the insight of Feynman and Stuckelberg in this was to choose the right pair. So now let's see what happens at this first pole. Let's evaluate that. All right, so yeah, we're doing that integral, and we argue that, let's see, so what did we say? So, so for Tx greater than Ty, we have K naught is omega plus I epsilon, K naught is omega minus I epsilon. Now, if the pole is at omega plus I epsilon, that's right, K naught here plus I epsilon puts the pole up here. So that gives G is 0. For minus epsilon, now we get the residue of this pole at K naught equals omega minus I epsilon. So what's going to happen, it will G of xy is going to be our coefficient here. Let's see. So what we want is the residue of this pole. So that's going to be this function evaluated at that root. So we have e to the minus I, K naught is omega minus I epsilon, Tx minus Ty, minus K dot, let me just call that delta x vector, just to keep this a little shorter. And that is still integrated over d3k.
You need the 2 pi I factor, right, as well? Oh, no, because you haven't integrated it yet. Yeah.
I'm trying to integrate. Now, this is a clockwise contour, so it's minus 2 pi I. So yes, your contour integral gives minus 2 pi I times the residue. This is the residue. Then we take epsilon to 0, so that's not going to do anything anyway. And we've got the integral. Now the remaining integral, I'm going to give some kind of name, but basically, let's see, all but the minus I. Let's keep the minus I. And this is for t greater than ty. Okay, let's see. So, and this is, yeah, I guess we can do plus or minus here. So this is the minus one, and G plus was 0 when we added I epsilon. All right, so for that solution, we get, and Tx greater than Ty. Okay, I see where we are. Now we do it all again for Tx less than ty. When tx is less than ty, this factor is negative. So k needs to, in order to converge, we have plus I k naught times some positive thing. So what we need for convergence is k to have a positive imaginary part. So now that means we have to close in the upper half plane. And now it encloses the other pole. And so again, we have these two cases when tx is less than ty. We close in the upper half plane, we get two more results. Now, let me see. These things correspond. Oh, this is messy working on this board. Let me see if I can. I'm just gonna name the rest of this as just call it some function. This is some h of x and y and t. All right. That's not the interesting thing. The interesting thing is whether t is greater than, tx is greater than or less than ty. Because what we get, now let me see if I can pull it out. Oh boy. Yeah, too many cases for me to keep in my head right now. It helps to be writing this out, and writing this out on the board is really messy. So let me see if I can list the various possibilities without trying to write it all down. I have written this all down in the notes, so it's there. But let's see, these solutions are positive energy solutions. These solutions are negative energy solutions. You know, K naught is basically the frequency, H bar omega is the energy. So these are negative energy solutions and those are positive energy solutions. Now, for each of those choices, depending which way we push the pole, we're going to get either something or get zero. And to list the possibilities, let me just skip ahead because we can do all the contour integrals you like, but here's the basic upshot. When we look at g of x, y, we have positive, give myself more room. We have positive energy solutions and positive time. All right, by plus t, I'm going to call this plus t and this minus t. All right, and let me explain that a minute. All right, ty is the time, the position in time, or the y coordinate in general, y alpha, is the space-time point where the source charge is. And Tx is the position where we want to know the field. So if the time at which we want to know the field is to the future of the source point, that's what I call plus t. I call it minus t if the source point is to the future of the place we want to know the field. And half of these green functions we're finding have that property, that they're non-vanishing when the field point lies earlier than the source point. So we're going to get these various possibilities, and I'll just write them down now. There's a step function in time. So this is for Tx minus Ty times some function of X and Y stuff here. The spatial integrals we don't need to worry about. And I'm going to call this H1. There end up being depending on which of these you're doing, there end up being two spatial functions, very similar, just differ by some signs. And then if we do this for positive energy, but in the wrong time order, we're going to have a plus theta. So theta is 1 if this argument's positive, 0 if it's negative. So this is the reverse time order. Then we have the negative energy solutions. That's these guys. And we have two cases of that too. So we have negative energy with positive time and negative time. And these are some closely related spatial functions, same h's. And finally, we have theta, the positive t, tx minus ty, and we have a step function of ty minus tx. And there's an overall minus sign. Okay, so basically, we need to put together one negative energy solution with one positive energy solution. Remember, those are the two poles that get added together to give the final green function. So we need to take one of these two with one of those two to have our final green function and predict the evolution of the field. Now, classically, what would we take? Classically, the impulse is to take the two positive time solutions. So if we take the difference of these to write our green function, then what we're saying is the effect at x depends only on, let me be explicit about this part. Remember what our solution says. We're saying that phi at x is given by integrating the green function at x, y times the source function at y. And we integrate that over all y. And so if we have the two positive time solutions, then these integrals are going to vanish this green function vanishes unless y is less than x. So this integral that basically runs over all time is only going to start at ty and integrate over times later than some source time to find the field at x. It only depends on the sources at earlier times. And that's the classical choice. And what everybody up to the time of Feynman and Struckelberg thought was the natural choice. But what they did was to choose one positive energy solution, one negative energy solution, but took the positive energy, positive time solution with the negative energy, negative time solution. And what that means is that, all right, this is going to have an effect on the field from times later, as if the thing is traveling backwards in time. And something traveling backwards in time, we've already argued, looks like to us moving forwards in time like a positive energy thing with opposite charges, opposite spins, and so on. So by choosing a different pair of green functions, by choosing the plus plus with the minus minus green function as the way to solve the equation with a source, they were able to interpret the negative energy solutions that invariably arise in quantum field theory as antiparticles, as particles with the opposite properties. So a negative energy particle traveling backwards in time looks like a positive energy particle with the opposite charge traveling with us. That's our experience of those negative energy states. So that is the Feynman-Stuckelberg interpretation of negative energy states. What else can I say? Yeah, I write it out here. Might as well write this out. So if I put plus E plus T, then this is going to be the integral from Ty into the future. And then I add the other case, and then I'm integrating from minus infinity to Ty minus E minus T times J. So we get contributions to phi at X from both the antiparticles and the particles this way. I don't know. I wrote down a whole bunch of stuff like this in this chapter 5. So read that. Come back with questions. We can do more contour integration because they're fun. If you want to see some of those. Take a look at chapter 7, then read chapter 5 of this book. So chapter 7 in the gauge theory book, and then read this chapter 5. I think the currently posted version is the edited version of that chapter. I've changed the sign on that mistaken Poisson bracket. And let's see, I don't know, because it's all so strange, I think I talked a lot about this, so I wrote a lot of text here. Just trying to explain it to myself. You know how people, when they're trying to explain something they don't really quite get, they say it over and over and over. Well, yeah. So you may find this section a little wordy because I'm, convincing myself that I'm saying it just right. So anyway, then yeah, I talk about chronicity, and I've talked about this in the quantum mechanics class too. The discrete symmetry of time reversal. In quantum mechanics, there are a few different ways of handling it. Classically, time reversal, you just replace t by minus t in everything. And, that's a discrete symmetry of Newton's second law, because Newton's second law depends on second time derivatives. So changing t to minus t doesn't change anything. You basically, have some solution x of t, you're just running it backwards. And that's also a solution to Newton's second law. But that is not a Lorentz invariant thing. You can't just, okay, so what that means for physical quantities in classical mechanics, like the momentum, all right, mv, v is dx dt, so you have a single t there, so momentum changes sign. Energy, a half mv squared, you got a t squared, doesn't change. So energy stays the same, momentum flips. Right? That's not what you're doing when you reverse time in space-time. So you need a different definition. It actually causes problems in quantum mechanics because if you look at what it means to preserve the Hamiltonian eigenvalue equation, it means that a time reversal has to be an anti-unitary transformation. So now this is quantum mechanics, not quantum field theory. So basically, if you do time reversal on I times some operator, so you do a similarity transformation to get time reversal. When this thing passes an I, you get a minus I. Okay, that's, I don't know, I'm still drawing thetas here. So it's called anti-unitary when it has that property. We don't have to do that in quantum field theory because we just flat out define time reversal. We actually define what I call it here is chronicity. You change the time component of all four vectors to minus. Now that changes energy to minus energy, right? It's a different transformation. So its non-relativistic limit is different than classical time reversal, but it is Lorentz invariant. The magnitude of any four vector is the same if you flip the sign of the time component because you're going to square it. So chronicity is what we have for time reversal. And basically, you know, if you look at the field operators we've been writing, we've got some amplitude e to the I omega t minus k dot x. If you do a parity transformation, that changes the sign of x. If you do chronicity transformation, that changes the sign of omega. So omega t minus k dot x goes to minus omega t minus k dot x. Now, if you do charge conjugation, well, charge conjugation corresponds to complex conjugation, right? We see it with complex fields. So now you change the I to minus I, and that whole Fourier amplitude is the same. It's unchanged. And basically, that's the gist of the CPT theorem. So the combined operations of charge conjugation, parity, and chronicity transformations, CPT, time reversal, it's called time reversal, parity, and charge conjugation leave just about any quantum field theory you can write invariant. It's a very elementary theory in a sense. It's very easy to prove in quantum field theory. And that's, well, that leads to some really interesting particle physics, right? You know, if you see something very violate parity and time reversal at the same time, like the weak interactions sometimes do, you infer from the CPT theorem that it also violates time reversal invariance, which means that that interaction does not flow the same way with the same probabilities if you reverse all the time direction, the time component of all your 4 vectors. So that has all kinds of cosmological implications and things like that. But I notice we're out of time. So yeah, happy to stay late, although the need for that, I guess, is not quite so pressing now. Let me, this afternoon, I will post the current version of the notes. I'm sort of halfway through Dirac theory at this point, and yeah, it's fun working through the Dirac stuff. It gets more complicated than scalar fields, but you know, it's not so bad. It's just a little trickier to isolate those mode amplitudes. So anyway, hang around if you've still got questions, and otherwise I'll see you, what day is today? Wednesday. So I'll see you on Monday, if not before.
We just email you the paper, the problem once we get it done.
Yeah,
Okay.
just, yeah.
All
Yeah, how are you working? Yeah, you doing, you handwriting or licks or?
LaTeX,
PDF?
yeah.
You what?
LaTeX, yeah.
LaTeX, yeah, okay, good. That's easy to mail. Yeah, that's a lot easier to read too.
Yes.
Good. Okay. All right. Yeah, just email it to me.
Yeah, you may not be happy with mine. It's all handwritten and sloppy. No, I'm kidding.
Yeah, I'm getting used to your writing, Alec.
Yeah, I'm just working on the homework too, so I should probably go finish that. So
Yeah, keep up, because you know it gets more complicated fast.
yeah, I'm all caught up. So I just have, I think I've got 3.
Glad to hear it.
Yeah, it's just the charge. It's just the charged fields, and then there's no more problems in just the complex field, right? And then that's the only problems, right?
Yeah.
Okay. Yep. I'm right in the middle of it. So.
Okay. What did you do to your head? Did you bash yourself? You okay?
No, I don't know. I just wasn't sleeping, so I just got stressed out and kind of scratching myself.
Oh.
I should just say that I fell. That's what I should say.
Yeah.
To be honest.
Yeah. Make it exciting. You were attacked by a ferocious tiger or something.
Yeah. No, it's not even my cat.
Yeah. Okay.
He doesn't get the blame. Shit.
Okay. Yeah. Just hope you're okay.
I am. Thanks, Professor.
Let me see. So you talked about transcribing those later field theory notes, and
Sure. Yeah.
I would love to have that stuff, you know, in Lix. Do you use Lix? Oh,
no, but I can learn. I mean, I do LaTeX, so LaTeX. So.
Yeah. Okay. I've got a bunch of conventions I use for spacing of indices and stuff like that.
Okay.
Which, you know, we should talk through. But, you know, what I'm thinking is, rather than try to listen to all those lectures, you just having the equations on the board transcribed
Sure. Yeah.
that might be an easier thing to do.
And then build the skeleton out.
And then, if all that's down, then I can go through and add text, as quickly as it would be to try to transcribe and figure out what I was saying. So, maybe that's the way to go.
Yeah.
And, pretty much the current half of the book ends pretty much at the first semester. So the Quantum Field Theory Notes 2 that I sent you.
Yeah.
I would say start sooner rather than later, because I think we're going to get to that stuff this semester.
Okay.
So if you've got a little free time and want to transcribe some things, let's talk about it. But I would love to be able to work through all of that, and then like all sorts of gravity theories too. So we will certainly keep talking in for a long and fruitful career, no doubt.
Yeah, absolutely. Yeah. Okay. That sounds great. I'd love to help how I can, and it'll help me learn to be both typing and the material itself. So it's great for me.
Yeah. Great.
And we'll see. I might get really busy here in a second because I've got a bunch of research grant deadlines and stuff.
I know.
But
I'm working on these notes as fast as I can, but I'm also trying to do 3 different research projects too. And I need to apologize to Eli because I haven't Zoomed with him, and I gave Noah a stack of reading, so he's busy. But anyway, anytime either of us can. I'm editing. I'm halfway through the Dirac quantization, and then I'll do E&M, and then then it gets into scattering. So then I'm going to be, as soon as I get there, I'm going to want to work with those notes from, it turned out it was the 2009, 2010 time that I taught this. It was a very good year for quantum field theory. I really wish I had those notes written out. So we'll get it.
Yeah, and give me, if I'm spacey or something and we're talking, just give me a reminder and I'll jump into it, because I need to work on my multitasking too. So
of course, it's like a break from something else maybe. Maybe the thing to do, it's easiest if you use LIX, because everything else is in LIX and you have to save having to convert it. LIX is a really nice LaTeX editor. It's a lovely front end for that. I would say the thing to do, when you get a chance to do something, do a page maybe, and send me that, and I'll go through and notice any typographical things that are my idiosyncratic spacings and stuff. And so, I'll send you a response to, clarify that.
Absolutely. Okay, I'll write a note.
Okay. You got a lot of notes up there.
I know, I need to clean them out. These are all really old. Two notes, just start. Okay. Yeah, I might need just something to not think about and type up, and then it'd be perfect.
Excellent. Great.
Okay.
That'd be great. Yeah, well, that would be a wonderful thing all the way around.
Cool. And I think, I know probably some of the other kids would be interested in going through it just whenever we all have time. So,
okay. So
don't get through in this class.
Yeah, I suppose, divvying it up in some sensible way, right?
Yeah, they probably all would like to be included. Maybe, I know Lyle and Guillermo are really gung ho. So
yeah, okay.
I too, but yeah,
yeah.
All of us have it too.
This is great. This is an exciting possibility, and you guys are a great class this year. You're all on top of it and moving along and enthusiastic. So this is the time to do it even better than 2009, 2010.
No, clear. Stop it.
All right. Well, I'm getting flooded with texts from my brother and sister who seem to want a car, and it's my sister-in-law's birthday and stuff, so I better,
You
you know.
bet.
Did you have any particular
No,
questions?
just that. Thank you.
Yeah. Oh, okay. All right. Great.
Have a nice afternoon, Professor.
So, all right. You have a good one too.
You're great.
I'll see you, Alex.
Bye.